Hi, welcome to my presentation. Sorry I can't be there with you all today. My presentation subject is on set theory, and in particular I wanted to focus on Venn diagrams. The areas I hope to cover today is why I've decided to cover set diagrams and set theory and Venn diagrams. Nervous? Venn diagram is part of the national curriculum. A little bit of the history of Venn diagrams and set diagrams generally. A little bit of notation overview, just to remind everyone of what set theory is. And then finally, a little bit about the restrictions that are placed on Venn diagrams based on the number of sets. So that's where we're going. So first of all, the first reason I chose Venn diagrams is prior to the MET course, I'd never heard of them. I'd done a little bit of set theory, but not used union or intersection, just used and or. And so I was interested in knowing a bit about it. But more importantly, not only did I not know about it, but as it's taught from Key Stage 1, every child I knew did. In particular, these two.
Mummy, Venn diagrams are easy peasy. Here's one we made earlier with our toys. These are the toys with wings. These are the toys for a pony. And these are the ponies that have wings. These ones outside are ponies or toys with wings.
So as you can see, it's taught from Key Stage 1, even little kids know what Venn diagrams are, so I thought it was about time I learned, which is why I did them. So, in terms of the national curriculum, it's taught throughout Key Stages 1 to 5. Venn diagrams come up in every single time. To start off, a little bit about my girls, they start off with really basic Venn diagrams with shapes and colours and objects, and just getting to sort data into groups. By the time we get to Key Stage 2 and 3, we've started putting numbers in, started understanding that it's an numerical thing. Usually, again, it's just groups of numbers like prime numbers and odds and evens, but getting more familiar with the maths involved. And then we don't really touch it much until we get on to Key Stage 4, where we start introducing it as part of the data handling area of the curriculum, with all the other sort of bar charts and etc, etc. And that's because it's going to come into Stats 1. It's not actually part of the maths curriculum, it's more statistics GCSE and also S1 in A level. So that's where it goes. It goes down the route of probability. So Roger, that's where sort of you're familiar with it, I'm sure. Okay. A bit about the history. So, logical diagrams have been around forever. I guess he's the most prolific mathematician in history. It's not surprising that Euler had his view on it. This would be an example of Euler's circle or Euler diagram. This shows that all clubs form part of the set black cards, and red cards are separate. That shows us that clubs are not red cards. So a nice easy way of representing logic. It was used for a number of years. And then we got to the point where there were these two gentlemen involved, and there were two different views on how to represent logic. This is John Venn, for those of you who don't recognise him, who the Venn diagram is named after, and this is Lewis Carroll, or Reverend Dodgen, who did the Carroll square. So we need to look at those two separately and understand them. This is a Venn diagram. It's very, very similar to look at to Euler diagram. This is what Venn said about the original Euler diagram. He said the weak point with the Euler diagrams and all similar schemes consist in the fact that they only illustrate the strictness of actual relationship to classes to each other, rather than the imperfect knowledge of these relationships which we may possess or which we may convey by the means of proposition, which sounds really complicated, but what that means is there's two key things that Venn did that are different from a linear diagram that make it a much more useful thing to do. The first one is a really, really obvious thing, but nobody thought of it up until then, and that was he put the rectangle around his circles. What the rectangle did was limit the data. So this is called the universal set. So in this case, this is a numbers example. The universal set would have been integer numbers. So all integer numbers would be the universal set. And then that enabled you very easily to put things outside the circles as well as inside. The other thing that Venn did, as well as putting the universal set into place, was that he insisted that all sets overlap each other. So in this case, you've got 2, and there's an overlap. If there's 3, it goes there, and there's the overlap there. So that was the uniqueness of the Venn diagram that makes it much more logical to use and much more complete. At the same time, so this was in 1880 that Venn was doing this up in the country, and then down in the city at the same time, Lewis Carroll of Alice in Wonderland fame was also looking at numbers, and he represented this exact same picture but using a square. So you can see that they're both really similar, and they're both widely used. Both of these diagrams are used widely in primary school still. The general viewpoint in literature seems to be that Mr. Carroll was much more logical, and you could extend it far beyond 2 sets. But Venn's diagram is much, much easier to use and much more visual and much simpler to understand. So both still used, but this one's considered far simpler and easier to use. Okay, so a little bit about brief introduction to set notation. I'm not going to go through it very much because partly because it overlaps what Adrian did before, and partly because I'm running out of time, and partly because I've given you handouts. You should all have handouts. Rachel should have given you all handouts. If she hasn't, she's frantically now giving them out to you. There's 3 pages there. The first 2 pages are some descriptions of various parts of set notation, and the third one I think might be really useful, which is why I created it for you specially, and that's loads of different Venn diagrams to show the different options you can have with the 2 circle Venn diagrams. So I'll refer to those as I go along, but feel free to keep those and put them in the back of your folder somewhere, and they might come useful, who knows. Okay, so the first thing we want to define is a set. We will call this just a collection of things. Each thing in the set is called an element, and we usually call it by a capital letter. So if we were going to have a set called Postmec Student, it would look like this in curly braces. So set A would be all of us in the group in curly brackets. So within the set, as we just said, there's an element. And if we wanted to say that something was an element of a set, we'd write it like this. So EMS is an element of A, or EMS is a member of the Postmec Student course. And then the last one on this page is a subset. So if we wanted to say that a set was within a set, so the example I've given there is my table with me, Rachel and Sophie, hello. We're a little set called B, but we form part of set A, the bigger group of people, and that's shown as B is a subset of A. Okay, so we talked about union with Adrian, and union is the equivalent, I guess, in computer terms of all. So if you've got 2 sets, one's got 1, 2, 3 in, and one's got 2, 3, 4 in, then the union is 1, 2, 3, 4. It's everything that involves both of them. So on your sheet, on the third sheet, you've got the 2 circles and they're both coloured in. So it's all. That's union, and it's shown like a U for union, nice and easy to remember. Intersection is the equivalent of and on your sheet that's the one with just a bit in the middle coloured in. So again, in our 1, 2, 3 and 2, 3, 4 sets, the intersection is 2 and 3. So again, this looks like a upside down N really. I think of it as an N rather, so I think of it as an and. The N in and or the N in intersection. Okay, set difference. This is where it sort of gets a bit more complicated. The difference between U and A are all the members of U that are not in A. So, again, back to our sets 1, 2, 3, and 2, 3, 4. The set union is 1. However, if we turn it the other way around and say that 2, 3, 4 is U and 1, 2, 3 is A, then the set difference is 4. So it's the first set divided by the second set, and again, we show it a little bit like that, U divided by A, so that's sort of how you remember it, set difference. And then the other one is the symmetric difference, and that is the difference between the two sets. I'm not going to read this out, it's quite complicated, but it's, I'll have a go. It's the difference between A union B and A intersection B, or A difference B U. Oh no, it's that. Anyway, it's very complicated. I'll give up. You can have a look at that at your leisure. It's in your notes. And again, we show that the symbol for set difference is a triangle or a circle with a line through it. That's probably actually that for you to read because I get lost. And the last one I just want to cover is power set. So you see the word power set quite a lot. If you've got set A, then the power set is all the possible subsets of A. So if we have A set 1 and 2, we've got possible subsets are the empty set, set of 1, set of 2, and set of 1 of 2. So we show that as PA with a curly P. And the form of dynamic subsets there are is it's 2 to the power n. So in this case there are 2 in my set, so there's going to be 2 to the power 2, which is 4, which is correct. And if there were 3, it would be 2 to the power 3, which is 8, etc., etc. So that's how you do power sets. It's every possible combination of subsets within a set. Okay, we're nearly getting to the end now, thank goodness. So that's set notation, and as I said, I wanted to focus a bit on Venn diagrams because I found them so easy and I've never seen them before. But one of the things that was really obvious straight away was the fact that Venn diagrams are limited, and they're really good if there are 2 or 3. We've seen lots of Venn diagrams of 2, but there's a Venn diagram of 3. Nice and easy. You've got 6. So you've got 1, 2, 3, 4, 5, 6, and then the outer bit. So you've got 7 options to use, and it's nice and easy to see. However, they do get increasingly complicated. So the formula, in fact, is for every set you've got n squared minus n plus 2. Which is, as I say, easy when you get to 2 and 3. When you get to 4, it starts looking like a pretty flower. 5, you get fairly lost already. And then the most I've ever been able to create a Venn diagram for is 11, and it looks a little something like that, which I'm sure you'll agree is far too complicated for words. So that's where Carol comes in handy, because it's much easier to have more sets in a Carol diagram, or in reality what normally happens is that we go right back to Boolean and we have a diagram that uses, because quite often we don't need all the intersections, so it's easy just to go back to this. And a nice diagram specifically for Susie's benefit. I included one with Guernsey, but that's a diagram that shows lots of different sets, so that's much easier to use. So I think that's really it as far as what I want to say about Venn diagrams. So in conclusion, one of the really good things about Venn diagrams is that you can use them in any area of life. So this is one I just thought would be appropriate for today. So the universal set is things I own, and two sets. One is what you pack for holiday, and the other one is what I pack for holidays in Spain. So in terms of the UK, I normally take with me an AA map so I don't get lost, an umbrella just in case, although I don't think I need it this week, and some pounds. However, if I was going to Spain, I'd need a passport, I need some money, thanks for that, Rachel. I need a suitcase, and in my suitcase I would put my flip-flops, put some suntan cream, put my Kindle on my phone. But one thing I definitely not need is my maths book. So, I'm all packed for holiday. You've learned a bit about set theories. Thank you very much for listening.